All right, so let's think about the effect of lenses on the path of light rays. Here's a simple concave flat lens. Let's say that we have a source, an object somewhere over here. So when we're doing these image diagrams, there is it's traditional to represent objects by arrows, and the direction of the arrow tells you whether it's right side up or upside down, and the length of the arrow tells you how tall the object is. This is because opticians, like physicists, cannot draw, and so an arrow is a great symbol to use when you seriously cannot draw at all. So before we get into the actual formulas we're going to use, let's talk about what rays of light from our object moving in different directions would behave like. So this lens that we have is a convex flat lens. So its focal length is going to be to the right, right? So the focal length of a lens can extend either to the left or to the right. But here, our focal length is going to be something like that.
Looks like a bow and arrow.
It does. It does, for sure. Okay. In your book, in section 25.6, there are some rules of thumb for how different kinds of light rays will behave. If we have a light ray that's coming from our object, and so it's coming from our object, and it's parallel to the whoa, I cannot draw a straight line. That is obvious. It's parallel to the axis of the lens, or the axis of the lens is defined by this little arrow, like from the bow and arrow, that connects the center of the lens to its focal point. Also, I'm going to make this arrow a little taller to make what I do next a little easier to draw. So if we have a light ray that comes in parallel, the effect is for that light ray to get refracted, right? And we know about refraction, right? So we could analyze this using Snell's law if we wanted to. And maybe you should think about it using Snell's law to kind of convince yourself that this is reasonable. But the effect of a ray that starts out parallel is that it is bent to go through the focal point. And this is for a particular kind of lens. We'll actually describe what kind of lens this is in a moment. But let's get some of these rays drawn first. If a ray comes a ray of light bounces off of our object and passes through the center of the lens, it does not get deflected. It just keeps on going straight. All right. So, with these two kinds of rays, you notice that they cross on the other side. And that point where they cross on the other side, that's where the lens creates an image. Right? So our actual object is over to the left. That's what we're looking at. But the image created by our lens is on the right-hand side here. And my ability to draw straight lines today is even worse than usual. Does anyone have a question or comment about these rays so far? Okay. So why would a ray going through the center of the lens not get refracted? So if it goes through the center of the lens, basically it gets bent a little bit as it enters the first surface, but then it gets bent back as it goes through the second surface of the lens. So we could work that out in more detail using Snell's law, but it's really similar to the problem you just did for the quiz, right? So it goes from air to glass, gets refracted, then comes out the back, gets refracted back. So if I was being technical about it, I would not draw this bit of the ray here because it's doing something a little weird inside the glass. But the net effect when it comes out of the glass is as shown here. Okay. So these two rays that we've drawn converge on a point on the other side of the lens. Because these rays converge, we call this a converging lens. This image is called a real image. Right? Note that it's called a converging lens will produce a real image most of the time. And the reason we call it a real image because the image is on the other side of the lens. So, light enters from the left-hand side of the lens. The image gets made on the other side of the lens. So the actual light rays that bounced off the actual object are making this real image on the other side of the lens. There are some quantities that we need to be careful to observe here as well. Other than the focal distance, this distance between the object and the center of the lens is referred to as the object distance. Funnily enough, apparently opticians do not have senses of humor. Their notation is extremely matter of fact. So object distance. Similarly, the distance from the lens to the image is called, you guessed it, the image distance. The actual height of the object is called the object height. And then the apparent size of the image is the image height. One of the things that we're most concerned about with lenses is how much magnification they provide. There's from this diagram, there's actually a simple way to define the magnification, and it's the ratio of the image height to object height. It turns out, and we're gonna see this in a little bit, but it turns out that ratio in heights is the same ratio as the negative of the image distance to the object distance. This negative sign, by the way, if magnifications are less than 0, that means they're upside down. As indeed, our image here is upside down. So we are expecting a negative magnification. At least the way I've drawn it as well, the image looks to be smaller than the object, so we would also expect a absolute value of the magnification to be less than 1.
Which is why if you take a magnifying glass and slowly move it away from your face, eventually the image in the glass will flip upside down the further away from your face it gets.
Yep, that is exactly correct. So this drawing is, we'd expect the magnification to be between 0 and -1.
Is that greater than or equal to?
Yeah, 0 is greater than or equal to magnification, which is greater than or equal to -1. So this is a converging lens. Does anyone want to tell us what the name of the other kind of lens is called?
Divergent.
Diverging, yep. So let's see what happens with a diverging lens. The focal length of a diverging lens is negative. And that means we're actually going to draw the focal length on the same side of the lens as the object is at. So there's the focal length. But we apply basically the same rules. So since we've got a diverging right here, on the converging ray, if the ray came in parallel to the axis of the lens, it would bend to go through the focal point on the other side of the lens. Slightly different for a diverging lens. If you come in parallel, then the light bends so that it looks like the ray came from the focal point. And if the ray of light actually does go through the focal point, it comes out parallel to the axis. Right, so the rays that come out of a diverging lens never meet. They do not form a real image on the other side of the lens. Instead, we do a backtrace to see where the rays seem to have come from. And that is where we mark the image at. And because the image, so we say here that what you see on the other side, on the right-hand side of the diverging lens, appears to be an object that is here. So this is where the object you're looking appears to be at. We call it a virtual image. We also use the same definition of the distance from the same definitions of object distance and image distance, except since the image, the quote-unquote image, is actually on the same side of the lens as the object. Right, we get the image distance is positive, the object distance is positive always, but for a diverging lens, the image distance is negative and the focal length is negative. Definitions of magnification stay the same though. All right, both of those considerations together lead us to a general relationship between image distance, object distance, and focal length of the lens. This is called the thin lens equation. I don't know about you, but it doesn't seem like anything called thin lens could be used to describe my glasses. But this is still approximately true for lenses that are as thick as mine. And it's a sum of reciprocals statement. So 1 over the object distance plus 1 over the image distance equals 1 over the focal length of the lens. And whether you have a diverging lens or a converging lens, this remains true, keeping in mind that a negative image distance means you have a virtual image on the same side of the lens as the actual object, and a negative focal length means you have a diverging lens. All right. Questions or comments on this bit? So notice we haven't said anything about mirrors yet. But mirrors basically behave the same way as lenses. Um, keeping in mind that light rays don't refract through a mirror, but they reflect off of a mirror. So if we have, say, a concave mirror, we've got an image. Concave mirror means that we have a focal length that's on the same side as the object. And then we can trace some rays, some light rays. So a light ray that goes through the focal length of the mirror, in reality, I mean, light rays don't pass through a mirror. They reflect off of it. But they reflect off of it. If it passes through the focal length of the mirror, it will reflect off of it parallel to the axis of the mirror. And if a light ray comes in parallel to the axis of the mirror, then it will get reflected through the focal length of the mirror. Which means our two rays are going to cross right there. So there's our image.
You said it reflects parallel to the axis of the mirror? Is that what you
Yes,
said?
that's right. Did I misspeak?
No, I just missed that last part, and I
Oh,
wanted to make
okay.
sure that that's what you actually said.
Yeah, so for a concave mirror, a ray that comes in parallel to the axis gets reflected through the focal point, and a ray that comes through the focal point gets reflected parallel. If you want, you can actually draw a third ray, a ray that hits the center of the mirror, right? The center of the mirror is basically flat with respect to its central axis, so whatever angle it comes in at, it also goes out at. That's the law of reflection. If we had the other kind of mirror, a convex mirror rather than a concave mirror, focal length is going to be on the opposite side from the object. And we get the same thing. So a ray that would have gone through the focal length of the mirror had not the mirror been in the way, that ray is going to reflect out parallel to the axis of the mirror. And a ray that comes in parallel to the axis, well, here maybe the easiest one is going to be if it comes into the center of the mirror, it's going to reflect out, right, at the same angle it came in at. Now these two reflected parts, they're not going to meet. It's just like the diverging lens that we looked at on the last page. Instead, we backtrace where those rays look like they came from. And there's our object. Okay. Same considerations apply since this image that gets formed on the right over here is on the opposite side of the mirror from the object. We say that's a positive image distance, right? And it's a real image. Over here, image distance is negative, and we call it a virtual. Also, a negative focal length on this mirror and a positive focal length on this mirror. The positive direction in lenses, right, is from the object to the lens or mirror, right? So that's the positive direction. So this for this focal length here, we're going from the lens to this point. Well, that's in the negative direction. So that's why the focal lengths, we call them negative. And the same, even though the formula that we brought out on the last page, we called it the thin lens equation. It actually works for mirrors too. All right. Questions or comments?
So it's called the real image, even though that image doesn't actually exist because it doesn't actually form behind the mirror.
Yeah,
Right?
the nomenclature breaks down a little bit when we're talking about mirrors. You're not wrong.
Okay. Making sure.
Question: why did I take this class? Because you are a curious and adventurous individual.
That and it's freaking fascinating.
One more thing I want to mention about nomenclature here. This 1 over f, this is frequently referred to as the power of a lens. And it's in units of 1 over meters. Right? So 1 over f, right? F is a length, so yeah, it's going to be units in 1 over meters. Except opticians got all fancy, and they say that for the purposes of lens, that 1 over meters is actually a unit of a capital D for diopter. And this is actually the first number on your eyeglasses prescription. So if you are nearsighted and you have, well, I don't know what everyone else's prescription is. My eyeglass prescription is a minus 7.25. That's 1 over the focal length of the lens of my glasses. So the focal length of my glasses is equal to negative 1 over 7.25. Where the negative sign means that it is a diverging lens.
That means you're nearsighted then.
Extraordinarily nearsighted.
And fun fact, also, pluses are very important in a prescription. That helps an optometrist and an optician to know specifically if you're nearsighted or farsighted and what kind of lens you'll need specifically.
Yeah. We will actually talk about the other two numbers in your eyeglass prescription after the break, I think. let's do one or two problems to kind of cement this, and then we will take a break and stretch our legs. Since we're talking about nearsightedness, here's a problem about nearsightedness. So your glasses prescription is -4 diopters. So you are nearsighted. You are reading a book. If you're reading a book or your phone or something, your the kind of usual object distance is between 25 and 40 centimeters. So the question
But your
is,
nose is long enough for you to read a book without your glasses?
I'm sorry?
Your nose, no, I would say your nose is too long for you to read a book without your glasses. Is that right?
For me personally,
Yes.
yes. Yes.
If you tried to get it that close, your nose would get in the way.
Yeah. So, yeah. So this is not something that I can personally do without my glasses. Your mileage may vary. Gregory, is this EC quiz? I don't know what that means.
Easy.
Oh,
Easy
extra.
quiz. Oh, extra credit. Sorry.
No, this is not extra credit. We're actually just going to work this together. So -4 diopters of a prescription means that the focal length of your lens is -1/4. And even though we're not asked about it, that means that the radius of curvature of your lens is 1/2 a centimeter if you had spherical lenses. But we don't actually need to know that much. We're not going to worry about that. Okay. So there's the focal length. You would like to hold a book at 25 centimeters away from your face in order to read it. If we had both the image distance and the object distance, we'd be able to get magnification, right? Because the magnification of a lens is the negative ratio of the image distance to the object distance. So we don't have the image distance, but we can actually use the thin lens equation to get it because we have the focal length. So 1/f equals 1/do plus 1/di. 1/f is -4. 1/0.25 plus 1/di. So 1/0.25 is, again, 4. So we have -4 equals 4 plus 1/di. So subtract 4 from both sides. -8 is 1/di. So the image distance is going to be -1/8. And now we can take that and put it in our magnification expression. So negative of -1/8 over positive 1/4. So the negative signs cancel, so we get positive, and 1/8 over 1/4 is 1/2. So in other words, the image is right side up because the magnification is positive, and it's half as big. Questions or comments?
It would be helpful if you drew a diagram of what you just did.
Okay, that's a
I follow the
great
numbers,
comment. You are
but that
absolutely
doesn't mean I know where everything goes.
yeah. What color do I want to use? Oh, there's no green on this page. So we have a lens here. Oh, you know what? It's a diverging lens because we're nearsighted. So lens is going to look something like that. We have an object over here. Because this is a diverging lens and the focal length is negative, right? The focal length is actually going to be like on this side. Notice the focal length is a fourth, and so is the image distance. So this object that we are viewing is actually on the focal length of our lens. And then the image distance is an eighth. So it's halfway along this distance. And because it's negative, the image distance is negative, we know that it's actually on the same side of the lens as our real object. All right. Does that help, Liz? Or Ms. Elizabeth?
Yeah.
Okay. Cool. Let's do one more question, and then we will have a break. All right, so we're photographing a mountain. I feel like a mountain deserves more than an arrow. I'm going to give it a triangle. Our lens is over here. And we're told that it has a 200 millimeter focal length. That's a positive focal length. So our focal length will be on this side of the lens. 200 millimeters is 0.2 meters. The object, on the other hand, is 10,000 meters away. And the mountain itself is 1,000 meters high. First question, where is the image? Is this a converging or a diverging lens situation?
Converging.
Yeah, for sure. So we're going to expect a positive image distance, and positive image distance means that our image is on this side, on the right side of the lens somewhere. So let's calculate how much that's going to be. Here's our workhorse for the chapter. 1 over f equals 1 over do plus 1 over di. The focal length is 0.2, so 1 over 0.2. The image distance is 10,000. Or the object distance is 10,000. The image distance we do not know. 1 over 0.2 is 5. 1 over 10,000 is 0.0001. Subtract 0.0001 from both sides. 4.9999 equals 1 over the image distance. Take the reciprocal of both sides. And you get 2.0 or whoops 0.200004. So it's fair to say that the image is basically on the focal length. In fact, this leads us to a useful approximation actually. If the object distance is really far, right? 1 over really big is approximately 0. So anytime that we have a really big object distance, it's okay to just, ignore this term. Right? Because 1 over 10,000 is just so much smaller than 1 over 0.2 that it's basically going to make no difference. All right, so once we have that, the magnification of a lens is equal to the negative of di over do, which is going to be 0.2 over 10,000 negative. So it's negative 0.0002. Nope, one more 0. In other words, this is going to be upside down and very small. Which it has to be, because the CCD on your camera is really small. You need to get that whole field of view shrunk down so that it can project the image onto the what's basically the retina of your camera. So if the magnification is 0.00002, that means that a 1,000 meter high cliff, right? So this is also equal to image height over object height. Right, so the image height is pretty small. Questions or comments? All right. No questions, no comments?